MEMS inertial sensors. Devices which are meant to sense inertial force are called as inertial sensors. Now let us see what is inertial sensor or inertial force. The force produced by the reaction of a body to an accelerating force is called as inertial force. It has the same magnitude but opposite in direction that of acceleration force because it's a reaction force. For many of the engineering applications, it's highly necessary to sense inertial force, especially in linear and rotary motions. Accelerometers are used to sense the reaction in linear motion, and gyrosensors or gyroscopes are used to sense the reaction in rotary motion. In the case of gyrosensors, the reaction force sense is called as the Coriolis force, Coriolis component. Now let us see few kinds of MEMS accelerometers and gyroscopes. MEMS accelerometers. Typically, MEMS accelerometers works based on the principle of spring mass damper system that we see in the case of conventional accelerometers. Because here also there is a proof mass, moving mass, or inertial mass, there is spring force, there is a damping property for the material. So the construction is similar to conventional accelerometers. Let us see the MEMS accelerometer how it works when it comes to micron scale. In all the accelerometers, MEMS based accelerometers, the acceleration of a body is sensed by sensing the displacement of proof mass. Let us see the construction of piezo resistive kind of accelerometer. As the name indicates, the movement of the proof mass is sensed by means of piezo resistive elements. Piezo resistivity means when pressure is applied, resistance for the element varies. For the variation in resistance is an indication of movement of some element or the stress developed in the element. The construction of piezo resistive accelerometer consists of a base plate, there is a cantilever beam, and there is a proof mass and substrate. This proof mass is a bulk micro-machined element, micro-machined from a substrate. In the construction, there can be the base as well as the top plate can be made of deposited by means of Pyrex. Now the working is, the accelerometer will be attached on the object to be sensed for its acceleration. Now when the object moves in this direction, say in this upward direction, because of the reaction, the cantilever beam along with the proof mass will be going down. When it goes down, a stress will be induced on this piezo resistor, thereby the resistance of the resistor will vary. So the variation in the resistance of the piezo resistor is an indication of the movement of the mass. In turn, that movement is a result of a reaction because of the acceleration. So piezo-resistive type of accelerometer works based on the movement of the proof mass to sense acceleration. Accelerometers are the second largest sold MEMS devices in the world. Another kind of accelerometer is capacitive type accelerometer. As the name indicates, the movement of the proof mass is detected by means of detecting variation in capacitance in a capacitive element. Here the principle of sensing is sensing the differential capacitance, and in capacitive sensing we know that there is inherent nonlinearity in sensing. In order to reduce the error due to nonlinearity, typically more than one set of capacitors are used in sensing with a capacitive method. So there can be two or more number of capacitors are used for sensing the movement or acceleration. As the number of capacitive plates increases, the nonlinearity effect can be reduced. Let us see the construction. Here there is a silicon wafer substrate that is bulk micro-machined to get a proof mass, and that is suspended by means of a flexor spring kind of element here. This is the mass, this is the support on which it is attached. So this silicon is enclosed between two casing, typically of Pyrex. Here you can see that on the top of the proof mass and at the bottom side of this top plate, there are conductive plates deposited, and these two conductive plates are connected in a circuit, and thus this becomes the two plates of a capacitor. Similarly, there you can see another two conductive plates. This forms another capacitor. So when this accelerometer is subjected to acceleration, that is, when an object on which the accelerometer is attached, if it is accelerated, suppose the object is moving in this direction, the down direction, the proof mass will have a tendency to go upward. What happens is the distance between the two electrodes here will come closer, becomes lower, because the proof mass is going upward, whereas the distance here it will be increased. So there will be two capacitance developed between these two and these two, so that the differential capacitance is sensed and the nonlinearity effect can be reduced to a certain extent. Another construction of capacitive type accelerometer is comb type accelerometer. Comb type accelerometers are a different kind of accelerometer, works based on the principle of capacitance. Here the proof mass is capable of free movement. These are placed on a substrate, but it is kept little away from the substrate. So it will be standing like this on that. So the proof mass is on the top and the proof mass can move comfortably. Only the lead point of this proof mass are attached to the base, that is on the circuit. Now on the proof mass there is a conductive material, and there are two other conductive plates are fixed on the base. So on the proof mass there is one conductive plate like this, and on the base there are two conductive plates like this. So it will be like this. Okay. So when there is a movement, the proof mass will move, whereas the fixed plate will be fixed. Again, what happens is when the proof mass moves, the distance between two plates are coming closer, whereas the distance between the same plate with the other one will be, other fixed plate will be increased. So let us see the working here. So here the proof mass which is capable of movement, it is connected to the base through flexor, some springs, and there is a conductive plate here. There are two conductive plates kept here also. Now when there is an applied acceleration in this direction, the proof mass will have a reaction in this direction, so it will be moving in this direction. The result is that this conductive plate will be coming closer to this, whereas the distance between this and the conductive plate will be increased. So here the capacitance is 1, here there is another capacitance. Again, if the two capacitance are sensed together, then we are sensing differential capacitance. As the number of capacitive elements like this are increased, say there is one more conductive plates from the flexor and another set of fixed plates on the ground, then again another set of capacitance happens here. So as the number of capacitance increases, the nonlinearity can be reduced, the sensing accuracy can be improved. When many this kind of projections are arranged on the proof mass, this will look like a conventional comb that we comb our hair. So because it will look like this, so that kind of arrangement is called as comb type accelerometer. We know that accelerometers are direction sensitive. That means if you keep the proof mass like this free to move in the vertical direction, then the accelerometer is capable of sensing movement only in the vertical direction. That means the lateral acceleration on the object cannot be sensed by this arrangement. Whereas you see in this case if it is capable of sensing acceleration only in the lateral direction, it is not capable of sensing the acceleration in the other direction. That means accelerometers are direction sensitive. So typically in devices, if the devices are meant for sensing acceleration in different directions, 3 dimensions, then they will be using different accelerometers for sensing the movement in or acceleration in different directions by orienting the accelerometers in different orientations. So this diagram shows a typical comb type accelerometer taken from the firm Analog Devices Incorporated. Here you can see that there are fixed plates, there are movable plates here. So this is what you see is a beam. So the distance between the beam itself is of micron range. So but that is sufficient to sense the change in the capacitance. So this is the beam, and what you see here is a flexor, and that is anchored on the surface. So there is a gap between the surface and the moving beam.